Okay, we're going to try to pull the whole concept of energy excuse me, together in a coherent formulation. Remember that the total work done on a system, on an object or system or whatever, by the net force is equal to the change in kinetic energy. That's what we did when we used the equation of motion and the Newton's second law to see that the net force times delta S is the change in the 1/2 mv squared. Work done by the net force is delta KE. Now the work done on the system by the net force, if it's positive, will tend to increase the kinetic energy. If we do positive work on the system by the net force, then the system, which exerts an equal and opposite force on whatever is working on it, will have to do the negative of that much work, so that the change in the amount of work done by the system is the negative of the work done on the system. Now if we change this work done on the system to negative work done by the system and then add that to both sides, this is what we get. This says that the change in kinetic energy is equal to the negative of the work done by the system, which is the work done on the system. Now that whole terminology is a little bit confusing and we have to work it through a lot of examples, but we want to try to see the big idea here, and we want to try to formulate things in such a way that we can keep some of this stuff straight. And it's a little bit hard to keep it straight at first. With experience and the application of some common sense, it gets easier. Okay, now, the work done by the system can be broken down into the work done by conservative forces and the work done by non-conservative forces. A force is, at least theoretically, either conservative or non-conservative. In fact, a lot of forces that we ideally say are conservative really aren't quite conservative. Elastic forces and so forth have a non-conservative component to them, but still this is a convenient way to break things down. Now what do we mean by a conservative force? A conservative force is one in which energy can be reclaimed. Okay, if I toss an object up into the air, if I toss this marker up toward the camera, I gave it some energy which allowed it to raise a little bit, and then it fell back down and regained that energy as it fell. That's a conservative force. If I press an object against a spring, I do work. When I release it, the object springs away, and that work that I did is reclaimed in the form of kinetic energy. A non-conservative force is one that dissipates energy. For example, if I slide the marker across the paper, I did some work to do that, but I'm not going to be able to reclaim that energy. The energy that I dissipated into friction is not going to organize itself, come together, and push the marker back this way, or forward this way, or to the side. We're not going to gain any kinetic energy from the energy that I lost to friction. So that, again, we see conservative and non-conservative forces. The work done by a conservative force we're going to call the change in the potential. The work done against a conservative force, I said by a conservative force. Let's do this again. This is work done by the system. That's the work done by the system against conservative forces, plus the work done against non-conservative forces. The work done against conservative forces is the change in potential energy. So that when I raise this marker toward the camera, I'm doing work against gravity. Gravity's trying to pull it down. I'm working against gravity, so I'm having to exert a force in the opposite direction of gravity, which is the force in the direction of motion. And I'm doing work on the marker against gravity. That work is my change in potential energy. Having done that work, if I release the marker, the energy comes back to me. And then the non-conservative forces, I'm going to lump into two forces: dissipative, non-conservative forces, and other external forces. Okay? And that's like if I push this thing, I'm exerting a force, and if I push it pretty hard, the force I exert is greater than the force of friction, I'm doing work against friction, and I'm also supplying an external force in addition to that. And we'll sort that out as we go. Okay, so as I've said, gravity forces are conservative. What goes up requires energy, and that energy is required to do the work against gravity. Excuse me. Coming down, gravity does equal work on the object, which it regains in the form of kinetic energy. I say here it regains the energy used against gravity to put it up. Okay? A spring force is theoretically conservative. It's mostly conservative. There's a little bit of friction, a little bit of energy lost in the spring. But the work to compress the spring is mostly reclaimed as the spring recoils. Okay? Friction is a non-conservative force. The work done against friction gets dissipated in the form of random molecular kinetic energy. As I slide the marker across the paper, there's some thermal energy created, and that increases the kinetic energy of the molecules in the paper and in the marker. And that energy is random, completely disorganized. There's no way to reclaim it. It's so disorganized we can't get it to come back together and do anything with it. We have the concept of entropy that's related to this, and I'll mention this now. It says that once energy becomes disorganized, it's not going to spontaneously reorganize itself. In every process, the disorganization of energy increases. Now that's a little bit of a blanket statement. There are microscopic processes where that doesn't happen, but in any macroscopic process, the net disorganization of energy cannot decrease. Energy can't reorganize itself. We have to do something to make the energy reorganize itself, and that's a concept we'll deal with much later on in the course.